Why her? Why not you? You're the one I'm hearing talking while I'm trying to talk. I'm supposed to throw things at her? And trust me, I'd know if Kate was talking, wouldn't I? Yeah, you bet I would.
I did this. You just said 6 out.
Kate.
See? Very valid.
Okay, where was I? Thank you, Kate. No, but seriously, grow up. Okay, anyway. Critton, you're completely justified, and I apologize for criticizing you. You as well, Sarah. Okay, let's carry on. Okay, so listen. You may have heard the term, you've seen it show up, even if we haven't used it explicitly yet, the term enthalpy of formation. It was in your last assignment package. And this is the enthalpy change when 1 mole of a compound is made from its constituent elements. Huh? What's that mean? When a mole of a compound is made from its constituent elements. Well, basically, it means this. If we have something, A question mark, B question mark, if we were going to make that thing in a synthesis reaction, what would we have had to make it from? A and B, right? And maybe those are diatomic, maybe they're not, but that's the basic idea, right? This is a formation reaction. It's a specific type of synthesis. It's a synthesis of something from its constituent elements. So no compounds to start with. If we were making water, for example, it would be the reaction where we make water by reacting hydrogen with oxygen. If we were making carbon dioxide, it would be the reaction of carbon and oxygen. If we were making lithium oxide, it would be the reaction of lithium with oxygen. Does that make sense? A formation reaction is just making a thing out of its constituent elements. And when we do that, it's associated with a delta H like anything else. But specifically, we say that it's the delta HF, because that's the formation. And then the naught, this little symbol up here, we'll talk about in a minute. For the moment, just chill out. In the back half, I'll have something for you, okay? Right now, you can work on what you want. You can kind of join in and see if you can help out, whatever. And then the back half, I've got a couple things. Is that cool? Awesome. Oh, actually, also, if you want to look through, I'm giving those tests back today, and just if anyone hasn't written it, then so be it. Sort that out. So my return pile is back there. Both. So if you want to look over there for what is chemistry and just return it, that would be amazing. So that tells us that's formation, like we see here. And then this symbol here is called the naught. And this refers to at standard conditions, what we call SATP, standard atmospheric temperature and pressure. And does anyone know what that refers to, standard atmospheric temperature and pressure? It's 20 degrees Celsius, so 298 Kelvin, and the pressure is 101.3 kilopascals. So it's just telling you that if you did this reaction under those conditions, now that looks like negative 298, but I'm just going to put maybe a dot. Or maybe I'll just do that. That works, right? Because the delta H of a reaction actually changes depending on what temperatures you do it at a little bit, and it can change based on what pressures you do it at. So if we're being really careful, we actually want to do these under known conditions. Does that make sense? So the result is that scientists have basically built a library of these things. Does that make sense? And so if you look, all of the possible reactions are here. Now, they don't show you the reaction. They just show you the compound. So let's pick one of them. And let's somebody pick one here. And which one? Silver chloride. Where's that? Down here. Okay. So for example, if we were to look at this one, what would this reaction look like? Well, if we were going to make a mole of AgCl in its solid form, what would we have to react? Ag. And in its natural state, what does it look like? It's a solid. We're always starting with the way things appear at standard atmospheric temperature and pressure. And at standard atmospheric temperature and pressure, silver is a solid. We're going to react it with what? Chlorine. At standard atmospheric temperature and pressure, what does chlorine look like? It's a gas, and not only is it a gas, it is diatomic. Now, for this to balance, normally we would put 2's here and here, but the instructions very clearly state that it's supposed to be how much is required to make 1 mole of this, right? So what number would have to go here? A half. Does that make sense? It's always for 1 mole. And what would the delta H associated with this be? Guys?
127.
Negative 127.0 kilojoules. Right? So if we make 1 mole of silver chloride out of silver and chlorine, it's going to release 127.0 kilojoules. Does that make sense? Do you want to do another one, or does that kind of make sense? Feels all right? Feels all right. Okay. Now, if you think about it, what did we just do? Well, we just looked at this and we were able to work our way into making a reaction from that, right? Does that feel okay? If you want to put that, sure. When you put it next to a reaction, we often don't put the per mole. You can, it's not wrong, but it's implied that it's the amount you get for this particular number of moles. But of course, this number of moles is 1. So if you want to put per mole, that's fine. And actually, if you want to exclude it, that's also fine. You'll see it done both ways. Is that fair? Does that answer your question? Cool. Okay. Sorry? I know. That's because I get a lot of random submissions of things at random times, and then I have to mark them. Well, you know how nice a test is when like everyone just does the same thing all in the same day? I'm just like, oh, that all came out the same day, and then I just sit down and mark them in one stretch, and then they're marked. Then you get this other thing, and it's like, oh, I got 2 of these today, 1 of them yesterday, 2 tomorrow. Anyway, enough about me. Okay, shh, listen. You may not talk about it. If there's anything not marked, just put it aside. I need to focus on this. Love you. No, it's all good. Love you. Appreciate you. You're doing work for me, and I care about that. But don't talk to me, all right? Yes. That sounded harsher than I meant it to. But just if you have questions, just hold them until I'm done the lesson, okay?
It wasn't a question. I'm just thinking all of this.
Okay, perfect. Well, boy, do I relate to that. Okay, look here. If I wanted to know the delta H of this reaction, all right? If I wanted to know the standard enthalpy of this reaction, right? Is this a formation reaction? No, this is a reaction I might want to know about. C3H8, what's that? Propane. This is burning propane. Well, here's a thing I could do. A thing that I could do is I could write a formation enthalpy for each of these reactions. For example, C3H8 is one of the things I need here, right? Well, how would we make C3H8? We would react 3 carbons, which at standard temperature and pressure is a solid, with hydrogen gas, which is a gas at standard temperature. And how many of them would I need? 4. Okay. Now, on the previous page, there ought to be a formation enthalpy for C3H8. Is there?
Yes.
What is it?
Negative
103.85 kilojoules. All right. What about, oxygen doesn't have a formation enthalpy. Because oxygen is, at standard atmospheric temperature and pressure, oxygen is a diatomic gas. So what's the energy to turn diatomic oxygen into diatomic oxygen? Nothing. It takes no energy. So O2 has no formation enthalpy. Because that is its standard form. All right, what about CO2? Shh. What about, that's okay. What about CO2? How do we make that? Carbon plus oxygen. And the nice thing about this one is it's pre-balanced, like that. Can we look on the previous page? What's the formation enthalpy for that? Let's go to the previous page. Let's look up carbon dioxide. Negative 393.5. And I'm going to color code these. Okay, and what about water? Could we do that? How would I make water? Yeah, hydrogen gas and oxygen gas. And of course, these are gases at room temperature. And let's be careful here, which I'm making liquid water, right? Okay. Can we look that up on the previous page? And you might find that there's two waters on the previous page, right? There's liquid water and there is gaseous water. But we want, in this case, the liquid water, which is? Yep. Are you looking for H? Yeah, I do that all the time. So it's 285.8, right? Negative 285.8. Yep, so we have to balance it. And to balance it, what would we have to do? Half an oxygen. Good. Okay. No, don't be sorry. Well, wait a minute. What have we just created for ourselves? Team, what have we just created for ourselves? We just made a Hess's Law question. We just made a Hess's Law question. So what I want you to do in the space below is use Hess's Law to figure out the delta H of this, our target reaction, using these three reactions. You don't have to worry about O2. In theory, what should happen with the O2? It should, well, not cancel. In this case, it actually should not cancel. We should end up, when everything balances out, with 5 of them, God willing, if we've done this right, right? So you should be able to use these three reactions to make that reaction. Can you do that? I'm going to give you, oh, sure you can. So ask yourself, is everything on the right side? Is everything in the right amount? And then get to it.
Oh, yeah.
You got this. I have faith in you.
Oh, we have to do it here because I have enough space.
By the way, Aiden, I saw what you were going for there, like the way you were kind of just working out in your head yesterday on your quiz. And if you notice, you were actually absolutely perfect. Everything you said was good. You just forgot to flip the signs on your delta H numbers. So you don't have to change your process. Your process is good. Just make sure you don't lose flipping those delta H numbers, and that will work for you just fine if that's a method that works for you. Does that make sense? Yeah. Like, I liked what you were doing there. It's just then it's like, oh, you didn't flip the sign. All right, so give that one a try. I'm going to give you 6 minutes. 6 minutes? Is that fair? What do you got for me?
So, bio says here, am I handing everything back that's marked there?
Yeah, give it all back. Okay. Thank you so much.
Unit grade 9 stuff and stuff that's not marked is right there.
Beautiful. You're the best.
And then, yeah, this is bio.
Beautiful. That was such a heavy sigh.
With a stack that's just back in it later.
That was just such a like.
There's nothing that cancels out.
Do they have to cancel out? What has to cancel out?
Like there's no carbons in the equation, so it should cancel. But there's like 2 carbons left.
Your carbons cancel. How many CO2s do you need?
3.
Okay. Did you change that equation so you'll get 3 of them?
Oh, I have to multiply 2.
There you go. There you go. You got this. You got this, Nana. I have faith in you. I have faith in you. I have confidence in confidence. I have faith in you. Ready to sing a song? Yes.
No.
No? Who said no? From Mary Poppins? Have you seen Mary Poppins? Yes. No, that's not Mary Poppins. That is Sound of Music? Yeah, so I have confidence in confidence. Mary Poppins is Sound of Music. You guys seen Sound of Music? Have you? You haven't seen Sound of Music? Dude, it's got everything a movie needs. Nuns, Nazis, music. What more do you want? All good movies have Nazis. This is the thing everybody knows. Nazis are not good. Nazis bad. Which is the thing that seems to be up for debate these days. But I'd like to say it shouldn't be. My clear take, Nazis bad. But like, the flip side of that is that a movie where people punch Nazis, good, right? By the transitive property of Nazis.
So you would put punch Nazis in a kids movie?
Yes! Yes, I would like kids to learn early on, Nazis bad, punch them. I'm a pacifist, I don't believe in punching people. I'm telling you right now, Nazi walks in the room, I'll punch him. And I have no problem with that. You can all punch him. We'll take turns punching him. Right? Like seriously. Like that is
Hold him down.
yes. Yeah. No, absolutely. No, but seriously. So I think like, I've been thinking about that a lot because I think like, Remembrance Day, these things become rote and you just sort of like, boy, geopolitics is tricky and war is ugly and messy and terrible. But it is worth reminding that like there are evil forces in the world and opposing them is important, and that's rarely a perfect thing. But, we know that war inevitably, whatever else it is, becomes the powerful inflicting suffering on the weak and the helpless. And, it's not the richest people's kids who go off and fight wars. It's not the richest people's kids who serve in our militaries. It is those who are disadvantaged. And it's not the rich and the powerful who get slaughtered when wartime comes. It's marginalized groups, and opposing that is important. So yeah, Nazi walks in this room, we punch him, and we take turns. And I know somebody who can hold him down while we do it. So there we go. Yeah.
Oh, I didn't look all the way through it, but a number on it.
I should have finished. I may have not put anything on it. If there's a section of your paper that isn't marked, you just bring it on up to me. Likely it means you got perfect on that, and I just got late. But just bring it up. Or maybe I got halfway through marking yours, and then somebody asked me a question, and then I put it on the marked pile, because that's a thing I do sometimes. So catch me after, okay? Catch me after. We'll finish marking that, and No, sometimes, guys, I'll be marking something, and then somebody will come up and be like, hey, I can't get the Wi-Fi on my phone. And then I'll help them get the Wi-Fi on their phone, and then I get distracted. Does that make sense? Okay.
You look very fancy today.
Thank you. You look very late, but I love you anyways.
I'm sorry, wait.
No, it's all good, dude.
Kartik, I have things for you.
Okay. Talk to me. How do we approach this as the Hess's Law question? What can we do? We're trying to get to this target reaction, and I find my little highlighter trick helpful. I don't know if you find that helpful, but that way I can look at these one at a time. C3H8, do we have the right number of them? How many do I need? 1. How many do I have? 1, but what do I notice? It's on the wrong side. So if I treat this as my little reaction A, what do I have to do with that? Shh, quiet. What do I have to do with it? Yeah, very good. I have to do -1 times that. I have to flip it. I have to reverse it. And what would that reaction look like now? C3H8 yields. I'm going to put that actually over here a bit, which may seem silly. But 3C and 4H2. And we know the delta H of that now will be what then? It'll be positive, right? Because if we flip the reaction, then it's no longer an exothermic reaction. It will be an endothermic reaction. But energy is energy, so the value should be the same. We flip the sign, but the value stays the same. All right, what about this little B reaction here? How's that going to work for me? Is it in the right place? Yeah, it's on the right side of the equation. That's where we want it. Do we have the right number? What do I need to do with that number? Times it by 3. Good. So that would leave us with 3C, which is a solid, reacting with 3 oxygens, which is a gas, to give us 3 carbon dioxides, which is a gas. And what would the delta H not be now? We're multiplying by 3, right? 5 times 3 is 5. Carry the 1. 2 times 3 is 9. That's going to be a 0. Carry the 1. 9 times 3 is 27. That's going to be 28. 28. 3 times 3 is 9. So that's going to be 11,805. Is that right? And it should still be negative, right? Cool. All right. Shh. What? And what about C? Is it in the right spot?
Yes.
Yeah, it's on the right side of the reaction. That's where we want it. But we need to multiply it. And what do we need? How many do we need? 4. So we're going to do 4 times reaction C. And that should give us 4 hydrogen gases. React with, what's 4 times a half? 2 oxygen gases to yield 4 water in its liquid state. And so we have to multiply by 4 again. That's trivial. 250 times 4 is 1,000. And then 35 times 4 is, well, 30 times 4 would be 120, so 1120. 5 times 4 is 20, so 1140. And 8 times 4 is 32, so 1142.3? 43.2 rather. A little spoonerism there. Do you know what a spoonerism is? Wasn't really a spoonerism. Spoonerism is named after a famous preacher, a preacher who wasn't famous, but he was famous for one thing, which is he had a habit of switching the first letter of words. So instead of like saying something was, a silly question, he'd accidentally say that it was a quillisestion. So a spoonerism of some sort. And I'll never forget my first day teaching ever. I was covering a class at Fort Erie, and I had to tell them that we were going to read a chapter of Huck Finn. But I committed a little spoonerism, and then the class found that very funny, and it was an embarrassing moment for me. But anyway, we'll move on. Never you mind. So, how does this work out?
This adds up to negative 2,219.
I'm sure that's true. But before we get to the... Well, okay, give me the delta H. When we add these up, what do we get? Negative 2219.85. And we only have one decimal place here, so that's just going to be 8, right? Okay, so we have a delta H. What about the reaction? What cancels here?
3 carbons.
3 carbons will cancel with 3 carbons. Good. Anything else? 4H2 will cancel with 4H2. And does anything combine? Yeah, 3 O2s and 2 O2s will give us 5 O2s, gases, and C3H8 is a gas, and 3 carbon dioxide, which is a gas, and 4 waters rather, which is a liquid. And what do we notice? That is, in fact, our target reaction. So, we figured out the delta H of a reaction by actually just looking at this chart. Does that make sense? Now, do you notice anything? Look at the equation we were trying to make, and then look at the numbers we ended up adding together. Do you notice anything? Could we save ourselves some work here?
Oh, so the O2 does not have a thing,
So the O2 didn't matter. And other than that, we looked up the formation enthalpy of carbon dioxide, and we used that number. Of course, what did we end up having to do with that equation? That equation we ended up having to multiply by 3. How many carbon dioxides did we have? Oh, and we multiplied that equation by 3. Interesting. How many waters did we produce? Okay, and what did we end up doing with that equation? Multiplying it by 4. Oh, interesting. Because we're saying, how much energy would it take to make 3 CO2s? Okay, well, we know that. Let's take how much energy it takes to make 1 CO2 and multiply it by 3. How much energy would it take to make 4 waters? Well, we know how much energy it takes to make 1 water. Let's just multiply that by 4. And then, what happened with C3H8? We were able to look up how much energy would it take to make C3H8, but then we didn't just add that number in. Before we added it in, we changed its sign. Why? Well, because in this reaction, we're not making C3H8, we're using it. We're getting rid of it. In this case, burning it, but it wouldn't necessarily have to be. And then we didn't have to say how much energy does it take to make gaseous oxygen at room temperature, because at room temperature, how much energy does it take to make gaseous oxygen? None. That's how you find oxygen. So you don't have to. So if you look here, did we have to actually do all the Hess's law work? Now, it's good to have done all the Hess's law work to show that this works, but having done it once, every time I go to an equation, do I have to set up 3 equations like this and then do Hess's law? Or could I know, if I know how much energy it takes to make water, as long as I multiply that by 4, I will be factoring in how much energy it takes to make 4 waters. And if I know how much energy it takes to make CO2, if I multiply it by 3, then I'll be factoring in how much energy it's going to take to make that CO2. And then, for our reactants, I'm not going to add their delta H's, because we're not making them. I'm going to, or we could just more simply say, instead of adding them, I should subtract them. Because instead of making these things, I am unmaking them. I'm using them. Does that make sense? And this leads us to, the coefficients in the equation told us what to multiply the equation, multiply the delta H naught F equations by. And then we flipped delta H naught F's of reactants, but not products. Does that make sense? So, with our formation enthalpies that we used there, it turned out that the multiplying we did was exactly the multiplying of the coefficients in the equation, right? Because the formation enthalpies are always how much to make 1 mole of that. So if your equation requires 3 moles, you just take that equation and you multiply it by 3. If your equation requires 5 moles, you take that and you multiply it by 5. The other thing we discovered is that because a formation enthalpy leaves the thing you're talking about on the right side of the equation, if you want it to be on the right side of the equation, if you want it to be a product, you just leave it alone. But if you want it to be a reactant, you have to flip that. Does that make sense? Formation enthalpies naturally put things as a product. So if you want to get it on the other side, you have to flip that equation. And all of that means this whole thing can be a lot easier. Formation enthalpies will be your best friend because we actually can simplify it. Ready? We're going to look at what we had before, and we're going to do the same thing for this reaction, but we're not going to do a full Hess's law. All right? We're going to look up the formation enthalpy for each thing. What is the delta H naught F of C6H6 as a liquid?
There's no CC.
Well, just wait. I can't because we can't.
49.
Just wait. We can't be copying this and doing the others. That's fine. We'll just give some time. We don't want to rush anyone. You know me, famously calm. Famously take my time. You know, roll with the punches. That's what I say. Live and let live. So, if we were to form this C6, if we were to form the C6H6, what's the formation enthalpy for that?
49.
Positive 49?
Yes.
0.0? Or just 49 as given?
49.0.
Okay. What's the delta H naught F of oxygen gas? Remember, we talked about this in the previous one. Oxygen gas? 0. Because that's how you naturally find this in its state. What about carbon dioxide? Okay, slow down. Sorry. You're too quick for me. Settle down. Give someone else a chance to look. Quiet, you. Someone else. What's the formation enthalpy of carbon dioxide? Yeah. Negative 393.5. That's very important. Do not miss a negative sign. There's a big difference between something that shoots out 393 kilojoules of energy and something that absorbs it, right? So we got to know which is which. C6H6 was positive. Is that true? Okay, someone else. New people. What's the formation enthalpy of water? And this one's water in its liquid form. Be careful about that. Negative. Great. Fantastic. Okay, now here's the deal. We're not going to make equations like last time because we discovered our little trick here, which is really how many, if we were to do the Hess's law of it all, what would we end up multiplying this one by? If we were to write this equation out, yeah, -1. We'd end up flipping it. This one, it doesn't even matter because it's 0, but we'd multiply it by -15/2. What would we multiply this one by? Yeah, don't write this. Don't write this. This is just for me. See how messy it is? Don't write this. What would we multiply this by? 3. Right? And it should all work out. It's going to work out. So, if that all works out, then what we're going to say is there's no need to do all that Hess's law. We have an equation for that. If we want to know the delta H of any reaction, we can just take, what does this symbol mean? It is a sigma. What's it mean? Yeah, add up the formation enthalpies. It's the sum symbol, so sigma means take the sum. Very good. Add up the formation enthalpies of the products, because those are all the things we have to make, right? And then, while we're adding all those, we're actually going to subtract all of the formation enthalpies of the reactants. And that's because those things aren't being produced. They're not being formed. So formation enthalpy is the opposite of what's happening to them because they're not being formed, they're being used. So if the formation enthalpy gives you a certain number, using it will be that same number, but the opposite sign, which means the easiest way to handle that is instead of adding it, subtract it. Does that make sense? So let's do that up above. Sorry, I should have left a little bit more room here, but that's okay. The delta H of this reaction would be what? Let's just go one at a time. Let's deal with our products. What are the products here? CO2, right? And CO2 has a delta H naught F of what? -393.5. But how many of those are we going to get? Okay, look here. In each of these, we're going to multiply it by its coefficient. Does that make sense? So this will be 6 times -393.5. That will take care of the CO2 of it. Good. We also want to take care of, what am I doing? We also want to take care of the other product. What's the other product in this reaction? Water. And the delta H of that is -285.8. So now sigma means what are we going to do with these? We're going to add them, right? And how many waters do we have? How many waters in this reaction? 3. So we'll say plus 3 times what is the delta H of water? Negative 285.8 kilojoules. Okay, now let's talk about our reactants. What reactants do we have here? Well, we have oxygen. Do we need to worry about it? Why don't we need to worry about it? Yeah, it has a delta H naught F of 0. So we can skip that. But what do we have to worry about? This C6H6, right? Which is probably benzene, but it could really be any... benzene would work. That's your most likely thing there, but it could be anything else with the formula C6H6. How many of those do we have? 1. What's its enthalpy? 49, but it's a reactant. So what do we have to do with that? We're not adding it, we are subtracting it. Does that make sense? And then we can just do that math. So do that math. This one I'm not going to try to do in my head. I mean, that's going to be 2,400 roughly, and that's going to be like another 800. So that should be like negative 3,300. Another. So we should be in like the negative 33, 3,400 range, but yeah. You're always subtracting it. Now keep in mind, it could be a negative number. And if you subtract a negative number, the effect is adding, but you're subtracting whatever that value is. If you prefer to think of it as adding but switch the sign, that's cool. Whatever works for you. Does that make sense? We'll do a few examples. What do we get? Negative 3,000. Great. And our unit? Great. And we don't get that 0.4 because 49 was a whole number. So we'll say 3,169, and that's kilojoules. And now we know the delta H of our reaction. All right, let's try it together. Somebody has made an error. I assume it was me. So let's do it together. How many carbon dioxides did we have again? 6. And what was its number? Negative 393.5? Yep. Plus 3 times negative 285.8, right? And then minus 49.
It should be like adding 49 in the end because you're multiplying 49 with negative 1, so it would be negative 49 instead of positive 49, no?
Either way, if you want to say plus negative 49, that's fine. Or if you want to say minus 49, those are functionally the same thing.
Would it be like plus 49 because...
No. No. Look here. The whole point of this, the way this is written out, we subtract the delta H naught F of our reactants. In other words, if this were being formed, it would add to the enthalpy, right? It's positive. So if it's being used up, it's going to make the enthalpy lower. However you want to conceptualize that is fine. But like, look at me. This is key. The delta H naught F of this tells us that to make benzene, the enthalpy has to actually be positive. This thing has to actually absorb energy. That's an endothermic reaction, right? 49 kilojoules. Well, if we reverse that, if instead we're using it up, now it will be negative. Using it up releases energy. So in this case, because it's a reactant, we're using it up. So that 49 kilojoules that it would normally release, we're subtracting that because this reaction is reversed. It's not being formed. It's being used up.
No, but the point is, shouldn't we, if it is negative, the energy is negative, then we tried it positive. You know, for this one, how it was negative, we made it positive.
Yep, that's what we're doing with this subtraction sign here. So don't do it twice. Don't do it twice. Does that make sense? That's what this negative sign here is doing. It's switching the sign of all your reactants. By subtracting that. Does that make sense? So if look at me, if you prefer to make it all addition and just switch the sign of all your reactants, which it sounds like that makes more sense to you, do that. Like, that's cool. That will mathematically work. So if you want to just add them all up, but say, I'm going to remember to switch all the signs of my reactants, totally cool. That will work just as well. Okay? But what this equation is saying is this equation is just doing it for you. It's just saying, instead of adding the delta H naught F of each reactant, we're going to subtract the delta H naught F of each reactant, which is doing the same thing you're doing. Put your hand down for a sec. I will get to you. The important thing is not to do it twice. Do you know what I mean? Look here. Don't flip the sign because you're like, oh, it's a reactant, I better flip the sign, and then be like, oh, and the equation says to subtract the reactants, because then what you're functionally doing is you're functionally flipping the sign twice, which is just putting it back where it was. Does that make sense?
Yeah.
So your instinct was exactly right, and then you looked at my equation and did what my equation said, and as a result, you were undoing it. Does that make sense? So you got to do it just once. So we're going to do it, yes.
Why did you want specify that's H and not F? You don't say like delta H not F.
Not
Yeah,
N-O-T, yep. Where did I write that? I wrote it somewhere.
Isn't that a degree?
Yeah. So be on time next time, I guess is the answer there.
Sorry.
Don't be sorry, be on time. Oh gosh, I am becoming my mother. My mother used to say, don't be sorry, be better.
Now it should be 3 to 6, sorry.
Which is a good line, right? Don't be sorry, be better. Sorry doesn't help me. Sorry doesn't put the teapot back together now, does it? No, it doesn't. I broke one of my mom's teapots once. Having said that, the number I get is 3,267.4, which tells me that, yeah, you just had that sign switched, right? Which, again, that's the problem you're going to make. So it is really important, don't outsmart yourself, right? If you're following the equation is helping you switch all those signs for you by saying subtract them. Don't then do double duty and switch them beforehand, and then the equation has you switch them, and then you do it twice. Does that make sense? And again, if in your mind it's more intuitive to say I'm just going to add all these together, but I'm going to know that I have to switch all the ones that are reactants, that's great. That is intuitively doing what this equation is formally telling you to do, and that's totally cool. So what do we get? 3267. 3267. Yes.
I know it's not needed, but like, could you also add parentheses around the products and the reactions?
And then just add them all together and then subtract it all at once, if you prefer. Absolutely. In fact, that is what this tells you to do officially. I always tend to just subtract each one. I kind of distribute that negative sign as I go. But if you prefer to add parentheses and then do it just all in one step in your calculator, totally cool. Totally cool. Well, let's look at this reaction. The reaction between salicylic acid and acetic acid to form acetyl salicylic acid. If we hadn't lost so many days, we'd have done this in the lab. It's a fun lab. You make aspirin. I want to know what is the delta H of that reaction, right? So in this case, the reaction is salicylic acid plus acetic acid yields acetyl salicylic acid. If you want to write out the full formula for each, you go nuts, but we're going to stick with this here. Is that fair? And I actually told you the formation enthalpy for each species involved. Yeah. And water, because what kind of reaction is it? What kind of reaction is that? Do you know? We have an acid reacting with, the truth is with another acid, but this actually, salicylic acid has an alcohol group in addition to its acid, and that's what's doing the reacting here. So it's an alcohol reacting with an acid. It's going to form an ester, and that's an esterification reaction, but we call it also a releases water. We call it a hydrolysis reaction. So there you go. So that's your reaction. I want you to tell me the delta H of that reaction. I'm going to give you, 8 minutes, 10 minutes. I want everyone to do it. Be a team. Work with your friends. Work with your enemies. Work with your peers. Work with your betters. Work with your lessers. I don't care. Just work. Yes?
Are we assuming that it's going to be one age?
This is a 1-to-1-to-1 stoichiometry, which you know from those organic reactions, right? You know that those ester reactions were 1-to-1. But that's a great question. That wasn't a dismissive response. That was a good question. Find your biotest.
I take because I won't be here third period.
No, that's great.
College applications third and fourth period today.
Nice.
And out of that whole stack, there's only one thing in there that's fine.
I'm sorry. It's a big stack. They continue to take people out of the college and university classes to help them apply to college and university. There's part of me that thinks, you know, it might be nice. Let's make sure they get in and are able to thrive there by having them attend class. That's what I think. Anyway. Got a lot of big opinions. What I should do is a lot of big shutting up. Yes?
I know this is the wrong class and you've probably been yelled at me, but have you returned my biologist report yet?
Any other questions? Okay, get to work.
Yes.
I have a question.
Do you have noodles?
I don't think I have some tomorrow. I'm sorry.
It's okay.
I'm sorry. I'm sorry. I don't have food for you. Having said that, get this question done. Whoa. I just had the wildest moment of deja vu. You ever have that? Yeah. Like where you feel like that exact interaction has happened. Like in my head right now, like just from me throwing something at Alex and telling Alex to get to work and then you coming over and like that whole thing, I was like, didn't I just do that? That was a profoundly weird mental experience I just had.
I have a statement. Or more of a thing to say to you.
It's not a question. Never mad at it.
Oh yes, I can.
So everything is organized.
Thank you.
This is chemistry, and it's like flips. So everything is something new. It's like
You're genuinely amazing.
this is bio. This is grade 9. This is.
You're amazing. Can I have the grade 9? I'll throw that back here, and then I will. Thank you so much.
That pile right there is stuff that's filled out and not marked.
Needs to be marked.
That stuff is random papers that have nothing in them.
Yeah, and I think it's all old enough stuff that it can all be recycled, right?
I don't know.
I think Sapphire Scott done probably not picking up her 0% on that lab. Probably she's decided.
Oh, I didn't even know that was the bottom of it.
Yeah, that's fine.
Yeah.
That is safe. Safe to recycle, I think. Okay, I want this question done. 4 more minutes.
So I didn't do it.
Yeah.
For H2O, are we supposed to?
Oh, what? Yes, and you can use your table for that. I had to give it to you for the other ones because they're not on your table. But remember, you have a table of formation enthalpies in this note, right? And we're going to assume that you've done this lab. Did it produce steam when we made esters? Any steam? Not really. I mean, maybe a little bit because we did it at heat. But mostly the water that's getting produced is liquid water. Good. And these would all be aqueous. Not that it matters. All right, get on it.
Do you want your stuff? Yeah. Might as well. Great.
What did you get for like the one you did? What did you get for the one you did?
Pardon?
Hey. Yeah. He marked it wrong.
I think so. Maybe not. I
Right,
don't
his
know.
favorite one is called.
I don't think so, actually. I think this is all assignments next. Very. No, I like
Doctor told me the other day. He said that if he gets a bad grade in his quiz and then he gets a bad grade in the entire course, he's just going to
Actually, I do like it.
You're not even failing.
We're in unit
regardless, I wouldn't have done this.
Yes.
Yo,
And then I would have
Like general and genetics and our
Random names. I'm running everybody I know, bro.
You also only one thing in that stat. Which is probably
so
impressive.
I have not missed a single day of school.
Calvin.
Since our
Each time I have a
late,
class.
zero absences. I've only missed 3 days this school year.
Oh, yeah.
And I know exactly which 3 days they are. They're in second semester.
Oh my god. So bad. I don't actually know if I've missed any days or not.
Wait,
I
did
can
you actually record it?
I think you missed one. I think. It should be
No,
on your
was it?
midterm.
I wasn't with her. I sent it to her.
Like right at the end after the donuts. Just like
What?
an
That
absence.
sounds exactly like Charlie.
But my absences and my late will have nothing to do with like my late is so
Remember I did that when I was looking at my knee and I just posted that song in my story. I thought that was the funniest shit ever.
Where did the head go? Oh.
I've missed one bio
You're trying to
class,
hide it the moment I say you.
but actually
know
when I
that.
was
Right
14
on
they
it.
marked me absent, but I was present.
Oh.
I was excused.
No, wait, where'd you get
Excuse
that?
you.
I was my absence once you made it marked me absent, but I was excused. I don't know.
Watch me
I
cook.
probably said excused, but you have to actually list
Uh-huh.
excused. They still click absent. So I've never earned
So no.
but I've been late to
So products. Okay, watch me cook. Okay. So like,
I have an idea.
oh shut.
It kind of is.
Yes, I'm glad.
No, it's half gym and half food. Like it's like gym though is like.
Would it be negative?
Like you were working with special needs kids and you're like leading.
What?
You are also participating.
What did he say?
Yes,
Are
I'm
they?
glad.
What did you say?
It's like, oh, no, it's not the English, like running or anything. It's fitness. Yeah, that's why I was like, I
What?
I'll
I love missing.
second semester as well.
What?
2 Englishes?
I'm doing grade 11 this semester, first period.
Oh.
Second semester, I'm doing first period. Grade 12.
Does that look okay?
So yeah, I've got two grade 12 courses.
Is that right?
this year, so
Does it spin in the show?
After the
second
plus,
period this semester.
add like
You have a line
brackets.
in the H.
What?
You have a
Add
line in the
brackets
H.
after this. No, the line in the H is right there.
There's no line in the H.
Yes, it is right
No, it's
there.
not. That doesn't exist.
Right there. Do you not see
That is
that right there?
That's a dot. That is not the line of
That
the
is an H. You guys are so like judgmental. This is how I draw my arrows. That's how I draw my arrows. And they hate it. I'm like, this equals. That's how I draw my arrows, Loki. So no. What does it equal? Did you not calculate it? No, I calculated wrong on my paper, and then I realized like I was kind of stupid. 589.9. 580 what?
Sunana, look what you get to hand out today.
It's okay, Suna.
It's okay, I organized it for you.
Thank you. Imagine you just don't know the kids in the class. You're like, what's your name again? I know, Sarah. Do you? Yes. See, does that line make you feel better?
If you don't know, just ask me. I know everyone.
It's negative 21214.3. Okay, in my head, it's like, remember how he said like the products would be, it's going to multiply by a -1, so it would turn like positive, because negative times negative is positive. So
Yeah,
that
it's the same thing, yeah.
So like in my head, I'm like, oh, let me remove it because it's times, like, you know, because it's the, you know, yeah. Cause like, you know how like it's like that if it's like that, and then you have to times it what the frick? And by like 1, and then if it was like originally like equals like I'm gonna make negative 85, right? So if you multiply it by like negative 1, it equals 80.
Yeah, I know that. But
Yeah.
you got the negative sign in front of that as well. So
Because you're subtracting.
no, but that's the switching of the signs. Is it not?
No, because this is subtracting. So you like remember how like it's still this in my head. It's still that, and then it's all that.
Are you changing
Can I
signs
say
twice? Remember the
So you know-
guys, look at this is the thing you have to watch out for. You can't switch the signs twice, right? The purpose of that subtraction sign is that mathematically what that subtraction sign is doing is switching the signs. So if you switch the signs yourself, just naturally, because you're like, I know to switch the signs, that's fine. Then just add them all together, right? But don't switch the signs and then subtract them, because then what you're doing is switching the signs twice, which we don't want to do. We want to switch the signs only once. And if I'm not mistaken, everything is negative here except the acetyl salicylic acid. Is that true? What's the acetic acid? Negative 624?
Yes. Yeah.
And salicylic acid's negative 589.
Yes.
And water is negative 285, is it?
Yeah.
Right?
Yeah. Where's water?
So,
That's
no,
water.
don't be sad. Look at me. No, don't
That's-
be sad. Be happy. Happy. You're good. Because you knew what to do. You switched the signs, right? That's what that negative sign is telling you to do. But don't then outsmart yourself and be like, oh, good, I switched the signs. Now to subtract them.
That's my crying puddle.
No, that's good. But
Can I
look like
fix
an
it?
answer.
Can I fix it?
Answers are good.
Oh, answers are good.
1744.1, that's what I got. If I'm wrong, then
1,
I'm sorry.
7, 4.
4.1. And I don't know why I got it positive.
That one?
I know why you got positive. Because, why did we get it positive? Because 2 of our reactants have negative delta H's of formation, which means that if they're being used as reactants, they're going to be positive, right? And then 1 of our products has a positive. The acetyl salicylic acid has a positive delta H not F. So it makes perfect sense, right? When you're said and done, you actually only have 1 negative number in that you're working with, right?
Oh, yeah.
Yeah, guys, did we do all this math with no units? Does that seem like something that I'd be happy with?
No, like
What are my thoughts on units,
if you
Steve?
imagine it in, it will always.
Gritton, what are my thoughts on units? They're good. Yeah, they're important. They're not just good. Lots of things are good. Fish sticks are good. The fish sticks aren't important when you're doing chemistry, though they're still good. I like fish sticks. I like ice cream sandwiches. I like those chocolate bars you can only get in American convenience stores, like they don't have them here. You know some of those? They got some goodies. They get different chocolate bars than we do. You go to an American convenience store, they got different options. And honestly, a lot of them not that good, but there's a couple that you're like, you know what? It'd be pretty good. I like I like combos. You ever have combos? That's kind of an American thing. Like little like kind of pizza pretzel snacks.
My mom loves those.
Yeah, those things are pretty good. But none of those things are important when you're doing chemistry. But here's the deal.
Yeah, they have.
I like units, and they're important.
We have those in Canada.
Can you get combos here?
Yes, they're at our at least they're at our corner store by our house.
Interesting. Might need to make a trip to your corner store.
Does it food that make you fatter or something?
Hmm?
He said they're different.
Like in America,
Yeah.
there's less regulation. So yeah.
Absolutely. Yes, I'm right.
Sorry, are you under the impression that America's a more obese country than Canada? It is not. Not meaningfully. No.
100%.
Oh, come on now. Obesity rates in Canada also very, very, very high. These are what they refer to as like the diseases of wealth, right? Like this is what you get in with easy access to high calorie food, which is obviously the envy of a lot of the world. And then we're communities of drivers, right? So we like to drive and not walk, drive and not bike, and we have office jobs, we work in seated positions, and yeah, we get heavier. But yeah, like Europe is like I think we come in a few percentage points under, but not to a degree that I would consider statistically significant. Like you got to go to Europe, you got to go to a lot of places to get rates than meaningfully than we have. And these are cultures, very walkable cities. That's a big one, right? Like a huge part of it is just like, does your day-to-day life, is it designed to include physical activity? Because it's all well and good to go to the gym, and that's great, and people should. But like, if your day-to-day life includes a good dose of physical activity, that's good. And it's also important to remember too that different body types make a big difference, right? So if you're from more equatorial conditions, then we would expect lower body mass indexes in general. And as you move away from the equator, up towards the poles or down towards the pole, we would expect that people's body mass index would be higher. And that actually isn't a sign of poor health at all. That's just a sign of expected outcome in places where having a high body fat percentage is actually beneficial, right? It's not beneficial to have a high body fat content when you look down at the equator because you're storing temperature, right? Like fat works as an insulator. But it's quite important to have higher body fat percentage as you move more north and more south, right?
You know what? He's recording.
Guys, we don't say shut up. I say shut up, but we don't say shut up. So let's erase that, shall we? God, shut up. How's that feel? Does it? Like, guys, this is a lot easier than doing Hess's law, is it not? You look it up in the thing, and you add them together. You gotta be careful not to outsmart yourself, but it's pretty straightforward stuff. So, much as I like your art, I do feel like it kind of interrupts the flow of our math, so I'm gonna lose it here. But we'll leave the happy one. It's nice and out of the way. No, you know what? I can go too.
Oh no.
That looks suspiciously like fun, and you know my thoughts on fun. Not a fan. Don't approve. Sorry? For history class. We're not in history class right now. Who knows? History class is fun.
History class is also for phones.
History's for phones. Math is for getting those trick shots in. Right. Geography is for picking up girls.
While yodeling.
Sorry? Handstands while yodeling. But science is serious business, team. All right. Science, we discuss such things as the relative merits of buffalo vis-a-vis lesser cities, combos as a superior snack, fish sticks and their importance. Serious business. So, this concept, being able to look up the formation enthalpies of a reaction, makes our lives a lot easier because we should be able to predict the change in enthalpy of any given reaction by looking up its formation enthalpies and doing it. Now, that is predicated on a few assumptions. It's predicated on the assumption that you're working at standard atmospheric temperature and pressure, right? And that there aren't additional reactions kind of happening in the background, whatever. But this is a useful tool. There's some homework on here. I'd like you to do it. I scanned it from a textbook because I liked it, but also you should be able to find most of the formation enthalpies for that in this table here. If there's one you can't find, you know what the nice thing is? Yeah, specifically, again,